Oh boy, have we something planned for today. If you own a Voodoo2 card, I'm 100% certain that you need to watch this video. We are going to debug two voltage lines today, 5 volts and 3.3 volts, and you will be amazed what we're going to find. We're going to find degraded caps, but we will also learn about the pyroelectric effect. And if you want to know what that is, then today's video is for you. I had no idea what it is, but these two Voodoo cards made me learn about it. As you may have seen in my previous video, these two Voodoo cards were not working. They crashed in games after about 30 seconds to 1 minute, depending on what title you played. For me, I didn't find any issues in Need for Speed Porsche or Unreal, but Unreal Tournament was a game that started to show issues. It could be because I used these cards for hours and then the issues started to appear more regularly. But if you haven't seen the video, it was the buffer chip that's here. You see it's still missing. I'm still waiting for replacements. But yeah, I could fix both cards by replacing the buffer chip here. Watch my previous video. I go really in depth trying to debug these cards, including removing TMU chips, swapping them, replacing the memory as you can see here, and doing all sorts of experiments by downclocking the card, disabling one TMU using the driver, and so on. So it's very interesting. But today, I think, is even more interesting. If you have a Voodoo2 card, this is preventive maintenance. Your Voodoo2 will fail eventually, and this could be one of the tips for preventive maintenance that you could easily do on your Voodoo2 card. When I started with this channel, I never thought I would get into diagnosing and repairing vintage hardware. But the truth is, a lot of our old electronics are broken or are failing. The real level up came when I started to design my own circuit boards. From Voodoo memory packs, to memory modules and wavetable emulators, to finally reach complex memory expansions for the Sound Blaster AW64. My journey would have been a lot different if PCBWay hadn't been there from the very beginning. PCBWay helps you to turn your ideas into reality by offering a wide variety of services, including CNC machining, 3D printing, sheet metal fabrication and injection molding. Of course, they also know pretty much everything about PCBs. Their cost-effective prototyping boards cost you next to nothing for 10 pieces with a fabrication time of 24 hours or less. My first project was a simple memory expansion board for Voodoo graphics. But this project opened up so many possibilities, and I kept building more and more complex projects. The next one might be a multi-layer PCB, hopefully completed in 2026. If you want to start your journey, head over to PCBWay.com and explore their services. You will be amazed how creative you can be. If you're heading over to PCBWay.com and create an account, you will even get a $5 welcome bonus. Perfect for your first order. You will find links to PCBWay.com and their shared project space with all my projects in the video description. And now, let's get back to our Voodoo cards. Let's jump right into the second card, which is this one here. The card works now, but the power delivery is definitely not okay. So let me show you what I discovered during the last project where I tried to figure out why these cards are crashing in games. I tried many things and got nowhere. So then I started to probe around the board and I might have found something. Let's have a look at our voltage regulator. This voltage regulator takes 5 volts in and outputs 3.3 or 3.5 volts. So if I measure the terminals here, this is our input voltage. This is 5 volts, and we can see that the resistance flips between kilo ohms and mega ohms, and then it settles at 25 kilo ohms. Now, this is our 5 volt input. This is our output, and we have 300 ohms. And I think this is the adjust pin because this is an adjustable voltage regulator. And we settle around 200 ohms. Okay, so this is a good Diamond Monster 3D2. Let's check the other card. So this is a card I haven't started any work on yet. Oh, only 75 ohms. This is on the 5 volt line. Something should get hot on this card. But let's continue. The output only has 43 ohms to ground. Also not good. And the adjust pin, 88 ohms. And this is the same voltage regulator that is on the working Diamond Monster 3D. So I wonder if you have a problem with the power delivery and if there is a problem with some capacitors or maybe with one of the chips that is on this board. I was very reluctant to put this card back into my system, but I did have the card in it before. This is when I discovered that this card suffers from the same artifacting issues like the first card. Even though I knew that this card had a power delivery issue, I had to power it on, pointed a thermal camera to it, and found a few capacitors that lighted up like a Christmas tree. So you've seen it. On this card, 3 components did light up. It is this capacitor, C125, this capacitor, which is C101, and this capacitor, which is C145. And if you can see this, something bumped this capacitor, but it's so not visible. And here on the resistor, so this is a 47 ohm resistor. We'll figure this out now. So let's move our caps to the side and see if we get a different reading on our voltage regulator. Oh my goodness, if this is all that needed to be done on this card, that would be amazing. I spent too much time on this one. Sometimes really it's just so much easier than you think. And I was trying to move TMU chips and things like this. Well, luckily on this card I didn't do anything like this yet. So, yeah. I just have to figure out which values these caps have. Let's measure the resistance of these caps now, because something needs to drop the resistance on our 5-volt line. So this is the big one, and we have 33 ohms. That acts like a resistor. This cap is dead. Let's check this one. This one lighted up, but it looks like this is okay. This one might be okay. And let's have a look at this cap. This was the hottest of the bunch. Yeah, 200 ohms, also not okay. These ones are most likely 100 nanofarad. So let's check capacitance. Nothing. Over limit. Next one. 100 nanofarad. This cap is good, even though it lighted up. I might actually replace this too. And here we have no reading on this cap. So these caps are bad. Let me see if I have some donor caps. Oh, I already took C125 for something else. And we take this one. C145. Okay. So let's quickly verify what values these caps have. 2.7. Okay. So here is our bad cap with 200 ohms. So this one goes out. It doesn't have any capacitance. And this one goes in. Okay. Also, this one goes out. And this one goes out. Here's our replacement part. And here's our last one. Done. Now the question is, what values do we get on our voltage regulator? Would be awesome if this would be fixed. So this is our input, 5 volts, should be moving up and down. We still only have 450 ohms, but that's much, much better from what we got before. Let's check our 3.3 volt output. 300, exactly what we need. 300 ohms. And the next one, 200? 200, great. So Still, this one here looks a little bit odd, but this is the 5-volt input. So, let's see if we can figure out where this is coming from, because I think this should be around 25 kilo ohms. Well, there were 3 capacitors that were lighting up. Maybe there are more. Can you believe it? There is one more. Okay, maybe this one is going to help us now fix our 5-volt rail. So I think it was this guy. There's nothing odd. It looks perfectly fine. I think it was this guy. 560 ohms. I think this is what we've seen on our voltage regulator. And this guy? Yeah, mega ohms. This one is okay. Okay, and... oh no, still. We still have more issues. How many caps are bad on this board? Wow. Okay, and here we are a few days later. I continue now after replacing the buffer chip. Unfortunately, the resistance has changed a little bit. Not by much, we still have an issue on this card, and this will be related to the pyroelectric effect that I mentioned at the beginning of this video. So, what we need is 20 to 40 kilo ohms on our 5-volt line, 300 ohms on our 3.3 volt line, and around 200 ohms on our adjust pin. So let's start from our adjust pin. We should get around 200 ohms. And yes, we still get that. And on our 3.3 volt line, we are getting 300 ohms. This is also good. On our 5 volt input, we are getting now 4.6 kilo ohms. Now, if we calculate how many milliamps this resistance is going to consume, then we get to 1 milliamp. And at this current, nothing is going to light up. So yeah, I need to come up with something else. But I do not want to desolder every single capacitor and measure it. I want to find out which capacitor is at fault and then just remove this single component. If you look at the back of this card, there are so many more. Each memory chip usually has one, a small one. Sometimes there are bigger ones. So yeah, I thought maybe I can figure it out by using the tools that I have. A multimeter and my hot air station. So my plan was to heat parts of the board and see if there is a change between our 5-volt line and ground. That is how I started with this, not even knowing that something like the pyroelectric effect exists. So first, let me experiment and then I'll try to explain what this pyroelectric effect is. Okay, ground is connected now via alligator clip here on my card, and our red probe is on 5 volts. So we get 4.6 kilo ohms. Now I use my hot air station, set it to 200 degrees and a flow rate of 20. What I want to do now is I want to pick one of the caps. Let's take a big one, this one here for instance, and blast it with hot air. So you see it went up by about 100, 200 ohms and then it dropped. Let's try that again. And then it settles down. Even if I blast it now with 200 degrees, it's back to 4.6. So it rises and goes back down. Let's try another one. Here's another one. It rises and drops. Let's try this one here. So, ready? 4.9 and then 4.5. So we're moving 300, 400 ohms. Here is one next to the SLI connector. Same behavior, all of them. They go up and then they go down again. 4.9 and then we are dropping again. Now let's have a look at smaller ones. Here's one isolated next to our FBI chip. Let's see what happens to this tiny one. And you can see it goes up a little bit, but then it drops again. So we reached like 4.65, I think. Let's try again. Yeah, and then it drops. So this is the behavior. And I went around the board looking for this. Now let's have a look at this one here. This is a big one again. First of all, oh. Did you see what happened? It jumped. Okay, it didn't do this before. What I wanted to show you is that it didn't go back down in resistance, but now it completely jumped to 5.5 kilo ohms. We were at 4.6. And you can see that it doesn't drop the resistance anymore. It just continuously rises. Now it goes back down because it cools down, but now we are at 5.5. Well, I'm happy that I still caught the 4.6 because it looks like every time I heat it up, it gets a little bit higher in resistance. That's why I went from the 800 ohms that we had initially to 4.6. It continuously rises. Oh, 6.7. Okay. We're always adding 1 kilo ohm. Okay, let's not do too much now. Let me explain a little bit more, and then we'll try voltages, because that's also interesting. So what we have seen is that the resistance is rising when the temperature increases. And this, I believe, is common knowledge. When temperatures rise, resistance rises as well. That is why if you have these overclocking contests, people try to cool down their CPU as much as possible to reduce resistance. But why does the resistance drop then? Well, and now we get into the pyroelectric effect, or pyroelectricity. This is a property of certain ferroelectric dielectrics. What it means is that the material in our capacitors spontaneously polarizes with a change in temperature, generating a transient voltage or current when heated or cooled rapidly. So what we are measuring here is the polarization inside our capacitor, and once it levels out, basically the material has polarized or adjusted to the new temperature, we're going back to a state of normal. But this transient effect is because of the polarization inside the capacitor. I hope I understood this correctly. If I explained something wrongly, please let me know in the comments. By heating a capacitor, we can measure how well it polarizes. If we have a damaged cap that, let's say, is in the range of a kilo ohm or 5 kilo ohms, this polarization doesn't happen as nicely as with a good cap, apparently. Without knowing the physics, I basically just looked for a pattern that didn't reproduce with some of the caps, or in my case, with one of the caps. Look at this one. This cap rises in resistance, but it never drops down. And this was my clue to have a look at this cap. Now, before I desolder this cap, I want to try something else. When the cap polarizes, it generates a transient voltage. So when we heat up a cap, we should be able to measure a change in voltage. So let's try that. I will put my multimeter now in millivolts range, and we will continue to measure between 5 volts and ground. Again, 200 degrees. And let's start with the same caps that we had before. So let's start with this one here. Now we are measuring the voltage. This is what I said about the pyroelectric effect. When we heat up one of these capacitors, it should expel electrons. Basically, we should measure a voltage difference. But of course, you need to get a capacitor that's on the 5 volt line. This is next to the memory, so I'm assuming this is on the 5 volt line. So let's see what happens when I blast it with 200 degrees hot air. Did you see that? 2.5 millivolts. And now we're negative. Now it pulls in the electrons again. This is almost like pressing a sponge, letting all the water out, and then leaving the sponge for it to suck back in all the water. The water being the electrons, basically. Let's try that again. You see? We jumped up and then it goes back down. This basically is when the material inside the capacitor has adjusted to the new temperature level and requests the electrons to come back. Let's try that again. 2.2 millivolts. Let's try another one. Here. This one, next to the memory. And 3 point something. Cool. Let's try a smaller one here. This one here, right next to the resistors. We're still in negative range. This means there are still electrons traveling back into our heated capacitor. This is what it means. At least this is what I believe it means. Please let me know in the comments if I'm just talking nonsense, by the way. Okay, so let's try this cap. There's another cap right next to it, so it might be 2 caps. But let's see what kind of voltage difference we can measure. Ready? And you see we went to 300, 0.3 millivolts, and then we dropped. And I think there was another one here, this one here. This is on our FBI chip. This is, well, there is another one. Well, let's see. So again, 0.3 millivolts, but then it went back down. This one. Oh, this one may be a larger cap. So it is important with what capacitance you're dealing with. So here we have a large one and here is a small one, but let's blast the big one. 2.5. Nice. And now let's see, in comparison, this guy here. Yeah, this one only went up to 0.7. Let's try again. I'm not blasting it right now. I will move the nozzle down and 0.5. We only went to 0.5. Let's try again. Yeah, it doesn't go there. It doesn't reach 2 point something or 3 point something. So, and this is what I believe now. This is our faulty cap. I tried to measure every single cap on this board. This is the one that behaves differently. Now, is it a lot of work? Yes. But wouldn't it be amazing to figure out which cap is faulty without desoldering every single one on those boards? Okay, look at the resistance. Now, when I touch it, obviously I will short circuit the component, so we'll go to 0. But then we should get a completely different reading on our multimeter. Let's see if that's true. There we go. And look at that. This is a normal circuit behavior. Now let's try to put a replacement cap in there and then we'll see what the reading will be, because I have a feeling we will stabilize. 2.5 microfarad. Okay. Okay, that was easy. And so yeah, this card settles at 35 kilo ohms now. Nice. 35 kilo ohms. We found our faulty component. How about that? Then let's have a quick look what this component reads. So this is the original component that was on the card. Let's first measure resistance and then capacitance. So we should get 6.6 kilo ohms. Oh, we got 3.7 now. Might be because of the heat that we added to this component. Okay, and now finally capacitance. And we don't even get a reading. So yeah, here is our faulty cap. And our Voodoo2 should now be fully working. Final test, let's measure all 3 terminals of our voltage regulator. And we start with 5.5 volts. And we have a resistance now off. But we should settle somewhere at 35 kilo ohms. This is what we had before. And here we go. 36, 35, 35 kilo ohms. Wow. Okay, next one should be 300 ohms. This is the 3.3 watt line. This seems to be normal. 300 ohms. And the last one should be 200. This is our adjust pin. If you don't have these readings on your voltage regulator, you definitely should try to figure out why that is. Those seem to be the correct values you should get on your voltage regulator. Okay, and there you have it. This is all I have for you today. Let me know in the comments if you think this was a really interesting way to identify faulty caps. I'm not sure if this works easily with every electronic component, but it did work very well on this card. Yeah, let me know in the comments what you think. Thank you PCBWay for sponsoring this video, and thanks to all my Patreons who are supporting this channel. If you want to become a supporter, please head over to Patreon and pick one of the membership tiers. You'll get early access to videos like this one. And yeah, you're supporting my work. Thank you so much for your time, thanks for watching, and I will see you in the next video. Take care and bye bye.